Hello Manu, how are you? Good morning. Where are other people? You can wait for one more minute and then start. Hello Chintan. I hope you all can hear me clearly and see my screen. Yes Manu, you are most welcome. Great. So I think people can join. We can start with the lecture today. So once again, a very good morning to all of you and a very happy Makar Sankranti. Uh, it had been celebrated yesterday, but many a places it is also celebrated on 15th. Remember, the Sankranti day has shifted towards 15th of January in last few years. I had read somewhere that around every 70 years there is a shift of a day and keep shifting towards the later part of the calendar. When I was a kid, it was definitely on 14th, but many a places it's now on 15th. By the time you people will be old, it will go towards 16th. Sankranti is a very important festival for us. In Mumbai, we don't feel much cold. A, because of a high population density. B, high pollution. C, proximity to the ocean or sea water. But rest of the India undergoes severe cold spell, especially for the people in the north. And the Makar Sankranti, the northward movement of the sun brings lots of warmth, energy, and freedom from the bitter cold. And that's why it is celebrated all over India. So, once again, a very happy Makar Sankranti to all of you. Going ahead, in the last class, I introduced about the noise in digital images. We talked about main source of noise and we talked about the other sources of noise, thermal noise, and different ways by which noise can creep in our images. Now, in today's lecture and the next few lectures, I'm going to talk about how to make the noise, how to control the noise, how to make it better, how to make our images free from noise. So let's go ahead with that. Today's class, we are going to look at image degradation model and noise models. The kind of noise models we are going to talk about are listed here: Gaussian, Rayleigh, Erlang, Exponential, Uniform, Salt and Pepper, and together they cover most of the different types of the noise. Sorry. So, image degradation model. So, the strategy to solve noise problem in an image is twofold. One, you take a ideal image or a good image and you corrupt it by the noise. And the second step is Since you only are corrupting the image by the noise, you know the noise parameters, and therefore you can develop strategies or models to remove that noise. So this study is done in an ideal manner. So as a student of DIP, we first take ideal image, add some noise, and then try to remove it and see if it works smoothly. Once we practice that, then we apply those principles to unknown images. I mean, images which we have not clicked, images which has already been corrupted with noise. So we take those images and solve them by the experience that we have got by our degradation studies. So that is how the technique goes on, two broad steps. So let me discuss those two broad steps again. A typical in spatial domain, typically you take an ideal nice image f of xy and you can degrade it. So you can degrade it a by applying some sort of convolution. Remember, we have done lots of convolution, averaging, Sobel, gradient, edge, etc. So you can take one of those h degradation function. I'm giving it a new name, calling it degradation function. So suppose if it is box matrix, which smoothens out. Smoothening is a can be visualized as a kind of degradation that you apply to your original image, and then you add noise to it. Remember, the noise is additive and not multiplicative. The new image that you will get, I will call that image as g of xy. That is my new image. Remember, here it's a convolution. The star represents a convolution, now which we are very well familiar with. So this is how a typically degraded image is obtained in the spatial domain. So two kinds of degradation. One is the intensity degradation. So you take intensity value and you change it either by a point transformation or using a matrix transformation, applying a degradation function. It could be anything, smoothing, Sobel, whatever. I'm just calling them as degradation function. So you can do that. This will change the intensity level. This has nothing to do with original intensity. Whatever is the intensity of the image, you add some more intensity fluctuations to it, and this is called what is called noise addition. So you add the noise specially from your side, and then you get a degraded image g of xy. The same thing can be written in frequency domain. We have already seen the frequency domain or the Fourier domain in the last class, so or last to last class. So f of xy, its frequency domain is f of uv. H of xy, its frequency domain is capital H of uv. You we have seen these filters, step low pass, high pass, band pass, notch. These filters can be multiplied to the frequency transform of the original image, and then this is the frequency transform of the noise. Remember, this is a function of xy and this is the function of u into u and v. Then you get a resulting image in the frequency domain, which is the corrupted image in the frequency domain, and then you can transfer it to the spatial domain. You can ask, why do we need to do this if you can do it in the spatial domain? So you can see advantage is visible on the screen. Very straightforward advantage. You have a convolution here, you have a multiplication here. Remember, the convolution in a spatial domain is multiplication in the frequency domain. So that simplifies your process actually. Reverse is also true. Remember, a convolution in frequency domain is equivalent to a multiplication in spatial domain. So that is how our model typically works, working model, that you take your image, you apply a degradation function, you add noise, you get a corrupted image, then you design your filters to restore the corrupted image. You design different kind of filters, see their effect, you get your restored image f cap, and then you compare f cap with f of xy. Since f of xy is available, you compare it with f cap. One of the simple way to compare is subtract this from this. If there is no difference, that means you have obtained the original image back, and that shows the efficacy of your filters that you have designed. If you feel that the final result is not same as the original, then you keep changing your filters. That is the way to proceed in image processing. Once you have learned, once you have experienced, then you can apply these filters to an image which is already corrupted before it has reached to you. So you don't have the original image, then you can apply that and you can be fairly confident that you can get some sort of good results. So what are the different noise models? The fundamental and the most important noise model I'm going to discuss is the Gaussian noise. Gaussian noise becomes most fundamental because, as I said, the most fundamental source of noise in an image is thermal noise, and it is well known that thermal noise is Gaussian in nature. So the Gaussian noise is the most important way to represent the noise, and a Gaussian noise is one of the most important noise that we have. This is the equation for the Gaussian noise. I read it: P of Z is equal, instead of P of Z you can just read Y is equal to, I'll come to P of Z a little later, 1 upon root 2 pi sigma e power minus z bar the whole square upon 2 sigma square in the limits minus infinity to plus infinity. Now here E is 2.718 approximately. Z represents intensity value. So Z can have any intensity value. Now remember, we are dealing with 8-bit images. The minimum value of Z will be 0. The maximum value of Z could be 255. Do remember that. So the Z represents intensity. Z bar represents the mean value of Z. So you can have between 0 to 255, you can have noise pixels of various intensity value, that is various Z value, which are governed by this equation. Z bar is the average value of the Z. Sigma is the standard deviation in this. So how does it look like? How does the graph look like? So this is how the graph would look like. The graph is centered at around Z bar, the average value, then it drops symmetrically on both sides. When all these is equal to 1, then this determines the amplitude or the peak here, and these are the half power points. That is the value at which, values of Z at which the intensity drops to half. So these are the half power points or half intensity points. I will show you that the majority of the pixels lie in this. But before that, let me talk a bit about it. This equation was is now called as Gaussian after the name of Gauss, German mathematician, very famous. You already know Gauss theorem, etc. And apparently, it was also known to Laplace independently and one more French person maybe 100 years before Gauss. So there are some controversies about whose name it should be named. We most likely you are going to encounter Gauss or Gaussian for this. The other name for this is normal distribution. This distribution is also called as a normal distribution, and normal is a noun and not an adjective. So it's also called as normal distribution, and it is applicable to many fields of studies. So I'm not getting into those details, but I would strongly recommend you to read through it so that you get a hang of this curve. This is single most important curve with from the DIP, which is applicable to many other branches of science, physics and others in general. So do study more, take any statistics book and it will give you a fair bit of an idea. Derivation of this is not in our scope, but if you put the values z very large and z very small and z is equal to z bar, you will get the points which are here, here and here. This is how it typically looks like. The two parameters which are most important here are the standard deviation sigma and the z bar. So z bar will define the position of the peak and the sigma determines the width of the graph. So for example, here I have two Gaussians or two normal distribution curves where the peaks are at the same place. So they have the same z bar. In this diagram, z bar is called mu. Please don't get confused. But their sigmas are different. Sigma 1 is greater than sigma 2. This is curve 1 which is wider. So greater sigma will give you wider curves. Narrower, lesser sigma will give you narrower curves. Here, two identical curves are two different positions because their average values are different, but sigma values are same. Here, the average values are also different, that is z bar is different here represented by mu, and the sigma values are also different. This is wider, so sigma is more. You can see that when sigma is less, it is narrower, but it is taller also. Here also you can see, and here also you can. So what is the reason? I'll tell you in a minute. So remember that it is bell-shaped, symmetric and continuous curve. Bell-shaped is obviously from the shape that it has. Symmetric, it is symmetric on both sides. If it is not symmetric, it's not Gaussian. It's continuous, there are no breaks, there is no dents, etc. Z bar is the simple average. Yes, yes, Manu. It's mean. For this curve, mean, median, mode are all at the center. So Z bar is also the median and the mode, not just the mean. It never touches the x-axis. Although the drawings that I have shown you, it touches the x-axis, but remember it tends from minus infinity to plus infinity. Practically, it will touch at infinity to x-axis, but since it is not defined, infinity is not defined, practically it does not touch x-axis, but still the total area under the curve is 1 or 100%, whichever scale you choose. And that tells you why once it gets narrower, it becomes taller. So you remember that if it gets narrower, it has to become taller because the area under the curve has to maintain to 1. If the width tends to 0, the height shoots to infinity. It acts like a delta function. And to tell you the most important, why is it called PDF or probability distribution function? It is called probability distribution function because area under the curve gives the probability. For example, probability that read x-axis as z-axis, probability that z will have any particular value is 1, which is the area under the curve. Probability that z will have any value between this center line and center minus 1 sigma only in this region is proportional to area in this region, that is 34.13% or 0.34. Probability that a particular z value is in this region is 0.13. The way you frame your question, what is the probability that I will get a particular z value from minus 1 sigma to plus 1 sigma? So you add the two areas. This is 0.34, this is 0.34, it will become 0.68. So probability that a z value in this region is 0.64. So whichever way you do, you can calculate by knowing the area, you can calculate probability. That is why area under the curve I'm talking about. That is why these kind of graphs are called as probability distribution functions. So, for example, you have done histogram is a probability distribution function. You have already learnt that. So it is something which is similar, just that we are arguing for a particular shape which is bell-shaped, symmetric on both sides, continuous. How would it look like in the images? So I have an example over here. Look at this carefully. You can see small dots scattered everywhere, very small dots. Now this is how the Gaussian noise will look like in an image. If you ask what is the mean value about which this noise is distributed, or the intensity levels in this noise are distributed, it's about z bar is 235. What is the standard deviation? It is 15. What does it mean? It means if you go to the previous one, you can see that between plus sigma plus 1 standard deviation and minus 1 standard deviation, you had 68% of the gray levels or intensities. So here the same thing happens. If you add 15 to 235, it will become 250. Subtract 15, it will become 220. So between 220 and 250, around 68% of the gray levels of this noise are distributed. Rest will be distributed beyond that. Centered at around 235. How do we get these figures? Very simple. In an image, you look at a region where the background fluctuations are minimal. You take the small sample of that part of the image and find its histogram. Look at how its histogram look like. So on this axis, which is the intensity axis, this is 0, this is 255. You can see a bell curve here. Background is white, so no other feature to describe to be described in the histogram. You are looking at only the noise. Noise is centered around this point, which is 235. Sigma is 15. I'll give you another example as well. Now you can see that here the Z bar is 126. You come towards the center of the scale. Since you have moved towards the middle of the scale, the noise is much gray now. So by looking at the grayness of the noise, you can guess what is the what is the peak value of the Z bar, or what is where the noise is located, where the center of the bell curve is located. That you can guess. With experience, it becomes very easy. Now here you can see that the fluctuations in black and white or gray and white is quite a large as compared to this. Sigma is double 30. So you can see that this is wider than this one. And then I have 160 and sigma is now 64. And you can see that the curve widens and you can place it anywhere. This is where the curve is placed at Z20, very close to dark. Sigma is again 15 as in this case. And you can see that the fluctuations are there in the very dark region. So these are the four examples of Gaussian noise, and the formula that I had shown you will help you to figure out the features of the noise in each case. What is the general strategy to figure out noise in an unknown image? Very simple. I did tell you, you figure out one part of the image in which the background fluctuations, image fluctuations are not there, which is particularly a single shaded, but with noise. You take a small sample, make a small rectangular box, crop it out, find the histogram, and from the histogram you will get the standard deviation sigma and the mean value. Once you obtain these two, then you can develop your strategies to remove the noise that we are going to discuss in detail in subsequent lectures, not in this lecture at least. So going ahead, I'm going to take some other type of noise fairly quickly. So the logic and ideas that we have developed in the Gaussian section, they will follow here also. So Rayleigh noise, next is one in line. Its PDF or probability distribution function looks like this. So you can see the difference between this and the Gaussian. The Gaussian was symmetric. This is not symmetric. On this side, it starts sharply at A, increases and then drops exponentially. Okay, so this is called Rayleigh noise. It is again a PDF, as in the case that at any point the probability of having a pixel value at some point is the area beneath the curve. Total area beneath the curve is still 1. This is how it is defined. For areas less than z equal to a, pz is 0, so all these is 0. And for areas greater than a or equal to a, it rises, reaches at a peak and drops exponentially. The peak occurs as a plus root of b by 2 and the peak value is over here. So the average of this, remember, it is no longer symmetrical. The average is given by this formula and the standard deviation is given by this formula. So this is the Rayleigh noise. So again, as I said, you take the sample of the image. If the histogram is asymmetric, most likely it is going to be Rayleigh and not Gaussian. The third kind of noise model, which is Erlang model, in which it looks more like a Gaussian, more like a Rayleigh noise, just that your left hand side starts at the origin. So this point starts at the origin. As z less than 0, it is 0. As z greater than 0, it drops, just that it also drops slightly differently. The amplitude is slightly different. Z bar is B by A, sigma square is B by A square. So this gives you standard deviation, this gives you average, and we call it as Erlang or gamma noise. Exponential, again further squeezing to the left. If you drop this dropping part of the graph and only look at this, then what you get is an exponential noise. An exponential noise is easy to understand. It has a peak value at 0, and then as z increases, you get continuously dropping intensities. At any point here, the probability of its finding is proportional to the area under the curve. So if I ask a question that what is the probability that z will have a value here, say between one interval marked here and here, then you take that area and that area will give you the probability. The z bar is 1 by a, this is the average in this case. Sigma square is 1 over a square, which is standard deviation. More simpler noise functions are uniform noise. As the name or the title itself suggests, it's uniform. It has a flat top, you can see. So what does it mean? It means that below A it is 0. So there are no noise pixels whose gray levels are below A. Above B it is 0. So there are no noise pixels whose gray levels are above B and they are 0. So all the noise pixels intensity levels are concentrated between A and B. What is the top part? You can see it's flat. What does it mean? It means that all the gray levels of noise which are between A and B, they have uniform probability of existence. So there is no variation over here. So this kind of noise fluctuations are called uniform noise fluctuations. So do remember that. Remember that the area under the curve is still 1. So accordingly the parameters are set. Please check here. This length is b minus a, which is width. Height is therefore 1 over b minus a. Width into height will cancel b minus a and b minus a, and the area will turn out to be 1. Average is the middle of the two, a plus b by 2, and standard deviation b minus a the whole square by 12. And if you want to calculate sigma, it will be under root. So that is the next kind of noise model probability distribution function. Salt and pepper noise PDF, that again we are quite familiar with. Salt and pepper, remember there's one set of pixels which has become white or very bright, other set of pixels which has become dark or very dark. Technically we define it in this manner. So for z equal to 2 power k minus 1, remember 2 power k minus 1 is the highest intensity level. For example, if k is 8, then 2 power 8 is 256, minus 1 is 255. So for z is equal to 255, it gives me the probability of the salt noise, very bright spots or white spots. How much PS you want? Generally, if it is a test image where you are implementing your noise, then you can control it. And if it is already corrupted image, then you have to measure it. So PS is the probability of salt noise, but salt noise is defined for the brightest value. Paper noise, PP, is the probability of the paper noise for the darkest value, defined for Z is equal to 0. So in the graph, this is the probability for the brightest noise, salt noise. This is the probability for the pepper noise below. They may not be same, do remember. You can have an image where the salt noise can be more scattered, more probable than the pepper noise, or vice versa. In fact, if you go to extremes, you may get an image where there can only be a salt noise or there can only be a pepper noise. For any in between pixel, Z is equal to V, which is in this section, any value between 0 and k minus 1, the probability is defined as 1 minus sum of the two. So you take this plus this, subtract it from 1, and you get the center. So this height is little bit of misrepresenting. Remember, it will all depend on what are the values of this side and this side. Typically, if PS and PP are very high, you get very less values in the middle. So yeah, so that ends our introduction to various noise models. We can stop our lecture today, and next class onward we will look into how to remove these noises from the image. Thank you. I will be joining the Google Meet in a minute.